Chapter 4.7, modeling data with exponential function and logarithmic function. Okay, let's say we have a set of data, so it has x value and y value. Once you plot those data, there are four cases. In this case, the graph of the first two is an exponential function, and the graph of the last two is related to logarithmic function. So when you plot data, then it should be similar. The point should be around this curve. Then we can try setting an equation that is related to exponential function. And if data is decreasing like this, as you see in the second graph, then we may think about the graph is related to exponential function decreasing, the exponential decay function, or if the graph, this time look at the x values. The x values is greater than 0, and then it looks like this, then we may assume that the graph is logarithmic function increasing, and this is decreasing logarithmic function. For the logarithm function, the x value is always greater than 0. For the exponential function, the domain can be negative number as well. So the exponential function is y equals a times b to the x. And then let's assume that a is positive numbers. And then based on the base b, if b is greater than 0, then the exponential function is increasing, as you see in the first graph. If b is between 0 and 1, then it's decreasing function. So the graph should be something similar to number 2. And the last two is about the logarithmic function. So a is just y value, shift ln graph, the logarithmic graph up or down. And if b is positive, then the graph should be number 3, it's increasing. And if b is negative, then reflect the ln graph across the x-axis. So you will be looking like this, number 4. So once you plot the data, consider whether the graph looks one of these 4, then we may try that the data is similar to one of these graphs, either exponential growth or decay, or logarithmic increasing or decreasing function. So actually we may think of this one, concave upward. If the graph is concave upward, then it looks like the first one. If we call this concave upward, and if the graph looks like the second one, then this graph is concave downward. So based on the vertex, the left side, if it's decreasing like this, then there's concave downward. This is concave upward. And if it looks like this, then these pieces are concave upward. And for the concave downward, from the vertex, it looks like this, and it looks like this. So if a curve segment looks like this, then it's either concave upward or concave downward. So based on this concave upward and downward, we can try whether the graph belongs to the exponential function and the logarithmic function. Also check the domain of x. So if that domain is greater than 0, then we may think of logarithmic function as well. So let's try an example. Example 1. There are two sets of data. So once you plot this data for each set, the set A looks like the first graph. So if you see this, the data is something like this, and this is a concave upward. Concave upward is, if it's a concave upward, then it fits graph number one. So it's more suitable for this data is exponential function. It's an increasing exponential function, so it'll be the most suitable for this data, A. And for the data B, once you plot this data, then it looks like this. This is concave down. So if we have a concave down, then number 3 is more suitable for this data. So number 3 is a logarithmic function, which is increasing function. So this data, for this data, is more suitable for the increasing logarithmic function. Then let's try example 2. Exercise 2, example 2. Okay, this is about the diamond. There is a data for each weight of the diamond. The value of the diamond is given. So this is the data. From this data, if we plug in the data, plot the data, then it looks like this. It looks like concave up. So exponential form. So since we are dealing with exponential function, and the logarithmic functions, this is more like exponential function. So once using a graphing calculator, plot this data, and enter the data and plot the data so that you got a graph of this, and it looks like this graph. So from this, we can set it up with an exponential function. And then it will give you all the values of the variables. So this is an exponential function, y equals a times b to the x. So the graph calculator will give you the values of a and b. And also there is r squared and r. Okay, r squared is a coefficient of determination, and r is, take the square root of r squared. Then r is the value of correlation coefficient. So correlation coefficient is the maximum value is 1 and the minimum is 0. So if the correlation coefficient value is getting close to 1 or negative 1, okay, 1 means positive, it's increasing. Negative 1 means the graph is decreasing. So if it's close to 1 or negative 1, then the data is very, the confidence level of the graph is almost 100%. So if it is 1, then all the data fits exponential, in this case, exponential function. If it's close to 1, there's more like to be an exponential function. If our value, the correlation coefficient is close to 0, then there's no relation to this function. So it is, since we have 0.99, which is very close to 1, the data is more like to be an exponential function. So the data, so exponential function, so the data actually fits the exponential function very well. So based on these values of a, b, we can have exponential function y equals 4067 times the base is 1.3816 and to the x power. So we have this exponential function. So that if a weight of a carat is provided, then we can predict the price of the diamond, which is similar to this product. So if there is a 3.5 carat diamond, then the price will be something like this. Just plug in this 3.5 for x, then y value will be 12,610. So this will be the price of 3.5 carat. So in this case, plot the data using a calculator, check how the graph looks like. So based on the graph, set the graphing calculator with, in this case, exponential function. Then it will give you all the values of the variables to make this exponential function, like an a and b. And then check whether the correlation coefficient, the value of r is close to 1. If it's close to 1, that is good. the data fits this exponential function really well. So using these a and b values, we have exponential function. Then you can predict by giving some value of value of x. Okay, let's try next one. Example 3. Okay, this is about the data for the times in the winning times in the women's Olympic 100 meters from 1960 to 2004. So from this one, okay, starting from, let's say 1960 is the x value 1. So now starting from x value 1, 2, 3, and so on. So x equals 1 represent the year 1960. If x equals 2, then that will be the next Olympic year, which is 1964. And x equals 3, then it will be 1968. So for each year, there is the time recorded here. So the data shows the number of the year and the time, the winning time. So based on this, once we plot this, then it looks like this graph. Looks like this one. Then this is concave down, something like this. And based on this graph, we can see it should be, we can try whether it is exponential form. If we go all the way up, concave down, so the graph can be number 2 or it can be number 4. So if it's number 4, that is a logarithm, decreasing logarithm function, or it's a decreasing exponential function. So let's try both exponential function and logarithmic function. So using a calculator, plot this data function. Then it will give us a data. So look at this correlation coefficient, the value of R. Since the correlation coefficient in logarithmic regression function is larger than exponential regression function, it's close. It's not actually close to 1, but it's more than 0.94, and the other one is 0.92. Since 0.94, which is the correlation coefficient of the logarithmic regression function, is larger than the other one, we may say that the logarithmic regression function provides a better fit to the data than the exponential regression function. So using the provided values a, b, we can write a logarithmic function y equals 61.93 minus 3.2926 logarithm of x. So in this case, we want to predict the time in 2012, in the year 2012. So we have to convert the year 2012 to the x value. That will be subtract 1960 from 2012 and divide by 4, because every 4 years, the Olympic held every 4 years, and then plus 1 because we started from 1. The x value will be 14. So just substitute this 14 for x so that we can find, predict the winning time in the Olympic 2012. So that would be 53.24 seconds. I don't have the data. Maybe you can check whether our prediction is correct. Okay, so all right, then let's try another one. Example 4 is related to a logistic growth model. The logistic growth model is the population limited. So as time passes, the number of, in this case, the population of deer, so the number of deers will be limited. Getting close to a certain number, and it cannot exceed it. It cannot exceed the number. Okay, so in this case, let's say x equals 0 represent the year 1990, and x equals 1 represent the next year, 1991. And then let's plug in this data in a graph calculator. Then the graph looks like this. So as time passes, since this is a logistic model, it should approach this asymptote. So this will be the value of C. And then use the calculator once you put the data, and then run the data for the logistic model. Then it will give you the values of A, B, and C. The carrying capacity is 3,965. So probably this horizontal asymptote is 3,965 years. Okay, and A value and B values are given. So this is the model for this is the logistic model. So based on this, we can predict the number of years in 2010. So 2010 is, so let's find x value for the year 2010. So we can divide the initial year 1990 from 2010. Then x value is 20. So just plug in, so substitute this 20 for x. Then the y value is approximately equal to 3,877. So these are the number of years that we can predict in 2010. So this is pretty straightforward. Plot the data and then run the data as logistic model. Then it will give us all the values. And then just predict the data, plug in the number for the given value of x. Then we can predict the number of years. Okay.